Okay, so optical property is absorption and emission of light. So because of this, some color of inorganic compounds we see. So this color, because of this color, these inorganic materials can be used as pigments in industry. Okay, in many industry, there's different demand of different color is there, because in for our clothes, we also need coloring, because different color of clothes we need some type of material which we can dye. Okay, some cases it is organic dye, but some cases it is inorganic. And see, like ink. So various color of plastic. So this plastic, they don't have any color, so you use this inorganic material, mix them, so that colored plastic or colored glasses, glazes, this we can produce. Okay, so these colored inorganic materials has huge application in industry. Okay, so this in long back historically, this pigments means normally these pigments originally developed from naturally occurring compounds, because before we don't have so much sophisticated laboratory to produce colored compound of our desire. So before, which is naturally occurring compounds, that only used, like iron oxides. So it can have various range of yellow, orange, or brown color. And manganese oxides, so purple and brown. Yeah, so this gives purple brown color. Then lead carbonate, which is white in color. See, white pigment is also very necessary in our different application that we will discuss later. Okay, so see, this white also a color. So in white thing, what happens? All the color in the visible range, all the colors is reflected. Okay, that's why we see a compound color. But this is also a white color. This is also a pigment. Okay, and vermilion. We use the vermilion. That is normally it is used mercury sulfide, which is red in color. So it is used as vermilion. Then orpiment, that yellow orange color. Then copper carbonates has a green color. Some are blue color. Okay, so these compounds are used, some previously in some people used to stay in cave. Okay, and people also draw the cave. Many drawing is, if you go to some historical places, so you can see some cave paintings. So this for these cave paintings, they used the naturally occurring compounds. So some of these compounds they have used for these paintings. Now. Which was first prepared, okay, the long back, like 3000 years ago, that was Egyptian blue, that is called. So it is a silica means your the sand. Okay, this sand only, but it is doped with calcium and copper. So calcium and copper doped silica, that is obviously made from sand and calcium carbonate and copper ores. So this was first pigment which is synthetically produced. Okay. So, but that is very long back, 3000 years ago. And in 2500 years ago, another was produced in lab, like that is called Chinese blue. That is also silica, but doped with barium and copper. Okay. Now, so already I have told that inorganic pigments is a result of absorption and reflection of visible light. So it has to be in visible light. If it is not visible light region, we cannot see any color. Okay, now let us go a little bit details on these things. So colored solid, this intense color of inorganic solid mainly can occur because of two reasons that you already have read about this thing. One is DD transition, one is charge transfer transition. And another type is there, that is called intervalence charge transfer. Okay. So these three type of transition gives rise of colored solid. So you have already know what is DD transition. So you know which this transition metal complexes have their d orbital splitted because of this different ligand approach. Okay, so this 5d orbital splits in T2G EG level that you already know. And so DD transition means from T2G level to EG level. this electron transition happens. And if it is happens in a visible region, you see the color. So these blue colors of cobalt alumina. See, alumina also white in color, and silica color. The sand color is also not any color. It is like yellowish, very light yellowish color. So this alumina and silica, when doped with other transition metals mainly, okay, this cobalt like copper. So this color of this two compound, the blue color, occurs because of DD transition in the visible region of electromagnetic spectrum. So this characteristic intense color of cobalt aluminate. This is cobalt aluminate. So sorry, this thing I didn't, the formula. This should be lowercase, the numbers. Okay, so this characteristic intense color of cobalt aluminate, this one, is a result of having non-centrosymmetric tetrahedral site for the metal ion. Now, DD transition actually not allowed. The what is the rule for transition? One is Laporte rule, and one is spin that one. Now, so two type of rule is there. So generally, DD transition is normally not allowed. Means Laporte forbidden rule. Okay. Why? Because they are same type of orbital. All are d orbital. So that is normally not allowed. But when you have a tetrahedral compound or tetrahedral site, like when you have octahedral, and if you compare octahedral and tetrahedral, so tetrahedral is having your means octahedral is having a center of symmetry in it. So octahedral, what is center of symmetry? I think, because if you from the center, if you pass exactly opposite direction, so you will get exactly same atom in the both sides. So it should have, that is your center of symmetry. But octahedral compound has center of symmetry, but tetrahedral compound don't have center of symmetry, because tetrahedral structure is not like that. It is, the structure is such, the three-dimensional structure is such that if you start from one atom, go through, pass through the center, in the opposite side, you will not arrive with the same atom. So tetrahedral compound don't have center of symmetry, but octahedral compound has center of symmetry. Therefore, as a tetrahedral compound don't have center of symmetry, that's why it is DD transition, or this Laporte transition is allowed for tetrahedral, not for octahedral. I think these things you already know, but sometimes octahedral compound also show this DD color due to DD transition because of vibronic coupling vibration. Okay, if a molecule is not a fixed bond, is not fixed, so it vibrates. Okay, because of vibration, that center of symmetry is not what I said. It moves. Okay, the center of symmetry moves, that compound no longer remains the perfectly centrosymmetric. Because of that, octahedral also shows, but tetrahedral compound is more intense color. Tetrahedral compound shows more intense color because this is a non-centric molecule, and it shows the transition. It allows the DD transition or Laporte transition. Okay. So this so now here, what is in cobalt aluminate? This cobalt resides in a tetrahedral site. Okay. So this removes the constant of Laporte selection rule. Okay, that means it will show the bright blue color. And if you don't understand anything, you can stop me and ask. Okay. Now the chemical and thermal stabilities are due to location of this compound is chemically and thermally stable. Alumina and silica is already a very stable compounds. Is this silicon oxygen bond in silica and aluminum oxide oxygen bond in alumina? These are very stable. Sand is very unreactive. Okay, alumina also like that. It is very unreactive compound. So these are very that's why it is chemically stable and thermally also stable, because it's melting this very, very high. Silica, this what is for, if you want to do some reaction, is very high temperature. Okay, like 400 or 500, then we use sand bath. No, You know, I think this sand bath used because this sand is having very high melting point. So we can use sand for very high temperature. So they are thermally also stable. So chemically and thermally stable, mainly though it is silica and aluminum. But we are doping this with some amount of transition metals. Okay, so because of this high chemical and thermal stabilities, and due to the location of this cobalt ion, that is I told tetrahedral site. Okay, so because of this, this color occurs, inorganic pigment, and this DT transition color occurs. Okay, and you see another example of this type of compounds like nickel doped titania. Generally, titania don't have any color. Titania is white in color because you know titanium is a transition metal. But it's what is the oxidation state of titanium here? Here it is +4. So in +4 oxidation state, titanium don't have any d electron. If there is no d electron, there is no transition and no color. So titania is white in color. But when you dope it with nickel, so nickel has partially filled d orbital, so it will show color. So nickel doped titania will show yellow color, and chromium oxide is green in color like this, and so on. So this is DD transition, and some yeah, and you know some compound shows charge transfer charge transfer transition, and because of charge transfer also very intense color is observed. So this example which are showing charge transfer pigments, that is like lead chromate. So you know this oxygen as a oxides as a ligand. Okay, they have fully filled orbital, low lying full filled orbital, which can donate its electron to the d orbital of the metal. So it is electron will move from the ligand orbital to metal orbital. Okay, so this is huh? Okay, this is ligand to metal charge transfer. Okay, so you know that is also two type. One to ligand to metal charge transfer, one is metal to ligand charge transfer. So when you have oxides, sulfides like this, selenides, here your transition is ligand to metal because ligand is having a fully filled orbital, low line. Low line means low energy level, which will be lower than d orbitals of the metal, transition metal. Okay, so this lead chromate, this is yellow orange, yellow in color. Okay, then yellow orange chromate, yellow orange. Okay, and this vanadate, bismuth compound of vanadium oxide. Okay, so this is also yellow in color. So this vanadate ion, what is the oxidation state of here? Here also, due to the doping of this bismuth, actually the color is coming, and the cadmium sulfide. Oh, sorry. Here also this. Sorry. Here to bismuth is not your transition metal. No. Here also charge transfer from oxides to bismuth, and then cadmium sulfide, cadmium selenide. This is yellow. This is red. Cadmium sulfide is yellow, cadmium selenide is red. So these colors are appearing due to charge transfer. Also very intense color which can be used as pigments. Now another type, what is third type, that is that I told mixed valence compound will have charge transfer. So what is mixed valence compound? So see, you can see this is, you have done some experiments where Prussian blue color comes. No. So this Prussian blue color, you have observed the color. What is Prussian blue? You know that. So this Prussian blue color appears due to this complex. Okay. Here you can see two iron is there having different oxidation state. One iron is iron 3 and another is iron 2. With this cyanide as a ligand. So because that is a mixed valence compound, because the valence is different for two iron, one is 3 and one is 2, that's why it is mixed valence compound. So in this type of compound, what happens, electron transfer between the two metal ions. Okay, so metal can also occur in visible. This transition of electron between two metal ions having different oxidation state that transition can also occur in visible region, and then you will see the color of the compound. Okay, that's why the Prussian blue is blue in color. Okay, dark blue. So this is widely used as a ink, because we use this blue color mostly for our writing. So this color is widely used as a ink. So you can see the structure of the Prussian blue, the crystal structure. Here is the structure of Prussian blue. Here you can see the iron ions. This is the iron ions are linked with the cyanide ligand. Ligand is your cyanide. So okay. So this is a structure. It is so on. There is showing. Students, you can hear me? I think it is so active. Can you hear me?
Yes, ma'am.
Okay, okay. Oh. Okay, now there is another compound having a royal blue pigment. We call it ultramarine. So this is this one having this structure. You can see this is aluminosilicate. So aluminosilicate is like alumina and silica. So if you mix both, like both is all silicon oxygen bond also there, aluminum oxygen bond is also there. That can be a aluminosilicate. That can be called as aluminosilicate. So if you mix silica and alumina, means aluminum oxide, and silica is silicon oxide. So if you mix silicon and aluminum, you get aluminosilicate. So this aluminosilicate is normally that is not having any color. So but in this compound, okay, in this compound you can see this crystal structure is also shown here. You can see this sodium ions is there in between, and sulfide H3 minus ion. Okay, means 3 sulfide makes a H3 minus ion. So these are there in between the crystal structure. So this somehow making some transition, electronic transition in the visible region. By this way, it shows a royal blue pigment, which is called ultramarine. Okay. So this is also one compound, a very colored compound having industrial application. Okay. It's a linked silica and alumina tetrahedra. So one silica will be there, another alumina will be there. Both are like tetrahedra, and they will be linked by oxygen. Okay, in the crystal structure. Now welcome. This is we discussed all about the colored pigments. Now we'll discuss some white pigment. What I told before, that white pigment is very important industrially also, because white color is needed in various application. So among this titanium dioxide, TiO2, that is extensively and widely used as white pigment. Okay, if you want to prepare some white plastic, then white paints the mostly we use for painting purpose, because white color, it don't absorb. Okay, it will reflect all this visible region color. That's why it is this you can keep the your building little bit cooler. Okay, so this is used for painting. Okay, so these all are white. Zinc, compounds, zinc oxide, zinc sulfide, zinc to transition metal, that but zinc is, in case of titanium, what is happening? TiO2, titanium is +4 state. So it is having 0 d electron. So therefore no transition, dd transition. But it can, suppose zinc, it is opposite. Zinc though having d10 configuration. So all are filled up. There also there also no possibility of dd transition. For zinc, it is fully filled. For titanium, is not filled at all, the d orbital. That's why generally zinc oxide, titanium oxide, zinc sulfide, and this is lead carbonate. That lead though is not a transition metal at all. So this shows your white color. Okay. Okay. if this compound would have some d electron incomplete, like partially filled d orbital, in that case they would have shown some color due to d transition. As they are not having d orbital, d electron, or having fully filled d orbitals, therefore no d transition, no color. So white pigment in the market, in which purposes is used? Paints, coatings, printing ink. Okay. So in case of ink, sometimes when other color also used, it is also combined with this white pigment to increase the brightness. Okay. Or generate a light color. If you are getting a deep blue color from some compound, make it little bit light using this white pigment, or also that will also becomes more brighter using this titanium is white pigment. So in also plastic fibers, okay, because our clothes, this is this fiber of our clothes that can be also colored. So paper, then cement, white cement, then even foodstuffs also this titania can be used, because this is very unreactive. Okay, so if you are using in small proportion, so it will not harm your body. So it is used for like icing sugar, sweets, processed fish fillets, and flour also. So sometimes to improve brightness or some other purpose, color and brightness. Okay, so now you can see white pigments is also having a large application. Now we'll just talk about black pigment, because as the white also important, sometimes black color also we need. So black pigments also important. So what in case of black pigment, what happens? All the color in the visible region is absorbed. Okay, for white pigment, all the color is reflected, but in case of black, all the colors is absorbed. That's why we see any material we see black, because all color is absorbed in the visible region. All the color is absorbed by the that material. That's why we see it is a black. So these are the normal concepts you already know, I think. Okay. Okay, so what is the most important and widely used is your carbon black. So this is nothing but your soot. You know, if you light up a lamp or this candle, also you can see the black soot. Now that is only the carbon black. But when it is manufactured industrially, it is the structure is little bit better defined. Okay, but that is soot only. So, so this is obtained how industrially they do it. But this black soot, when you get this black soot, when you do partial combustion of your hydrocarbon. So any fuel, whatever you using for lighting up, that is to your hydrocarbon. This candle also hydrocarbon. But when some you do that time, though little bit should appears, and most of this thing oxygen used is, and it gives light. But if you want to prepare more shoot industrially, then you will do the partial combustion, means you will do the combustion by heating, but absence of air. Okay, if it gets more oxygen air, then it will not give much shoot. So you have to do in absence of air. So that is called pyrolysis, and you can get carbon black in lot of amount. Okay, so this is also having application in printing inks, paints, plastic, rubber. Means application is same. As you need white color also, you need black color also, and you need also other colors. So this is copper chromite. Okay, this is also frequently used as black pigment. This is one example. And what is the drawback of these black pigments? They absorb all the light in the visible region, but it also absorbs light in the infrared. Okay, infrared region also they absorbs that light. That means if it absorbs the infrared, you know, infrared always heats up anything. Okay, if it absorbs the infrared light, it will heat up the particular compound. Okay, so that is the problem because it shows black color but also heat ups that material. Okay, that is your drawback because if you are preparing some material, it is not always desirable that you get heated up that compound, whatever product you are using. Okay, you don't want that one to heat up. So that is one drawback. Okay, so that's why there is this research to develop new materials which will absorb only in the visible region but will reflect the infrared wavelength so that you get the black color also and not also heated up. So this is one example. Okay, this compound bismuth manganese oxide. Okay, this is exhibits this property, black but not increasing the temperature. Okay, so this is all about your colored compounds application as a pigment, how we are getting black color, how we are getting white color, and how we are getting different colors because of different type of transitions. This is as a summary. So one is Didi transition, one is charge transfer transition, one is intermetallic valence electron transfer. Okay, so that is three things. Now, this absorption of light, this property of inorganic material can be also used in another application, that is your photocatalyst. Okay, so what are photocatalysts? Nowadays, this photocatalyst is very important thing because of this applicability. This is wide applicability. So that means from the name itself, you can understand this is photocatalyst means obviously related with photon, that is your light energy, and catalyst means it's catalyzing some reaction. Okay, so why photocatalyst is very desirable reaction because here you don't have to give heat energy for a particular reaction to catalyze, but if you just give a light, that can catalyze the reaction. Okay, so 1 minute. I think okay, after 5 minutes, maybe this meeting is going to end because here they give only 40 minutes. So I have 5 more minutes to discuss. Okay, I'll discuss that. After that, if some portion is remaining, so we can discuss that in the next. Okay. 1 minute, just. Oof. So in photovoltaic, that material which will act as photocatalyst, that can be called as photovoltaic material. Okay. So what happens in this means inorganic pigment, what is happening? Light is absorbed and re-emitted. Some light is absorbed, then re-emitted, then only you can see the color, no? Because it re-emits some energy. Or it turns into the vibrational energy or heat. Okay, but in photovoltaic material, what happens? The light energy excites an electron, and the separation of this electron means the electron separates from that particular material, creates a hole, and then the electrons don't recombine immediately, means it don't immediately go to its original ground state. Okay, then it gives but it gives because of movement of this electron and a hole created by that electron, movement of this will generate electrical current. You know, electrical current is nothing but the movement of electron. Okay, when electron travels from one place to another, it can give you electricity. Okay, so here when inorganic pigment case, the electron just excites from one level to another, then it comes back to its original level, it re-emits the energy, you can see. But here it will excite in a means from valence bond to excite to conduction band. Okay, you know band system, you know band, this bands are created by orbitals in different level. Okay, so when electron is excited and is separated from that particular compound, and it moves from one place to another, creates a hole and don't recombine, then it generates electrical current, and that is the basic thing which is needed for a photocatalyst. Okay, so what we use the titanium dioxide, that can be also used as photocatalyst. Okay, it is also used as a white pigment, but it can also be used as photocatalyst. Okay, so it is having a wide band gap. That is, you can see the band gap is 3.2 electron volt. So the band gap is also expressed in terms of energy, because how much energy is needed from valence bond to go to the transition bond, conduction band. Okay, so titanium dioxide have different type of crystal structure. One is called anatase, another is rutile. So because of different crystal structure, they have different this band gap energy. One is not very different. This is in anatase case, it is 3.2 electron volt. Rutile, it is 3.1, not very much. So leads to absorption of light with wavelengths which is below 390 nanometer. That is remains in the UV region of the electromagnetic spectrum. So this energy is very sufficiently high to split water. You know, last day when I was teaching this hydrogen storage material, what I told, why hydrogen as a fuel is very demanding, because you know, hydrogen, if it is oxidized, it will generate only water, no carbon dioxide. So we want to reduce our pollution. So carbon dioxide we don't want to use. So when hydrocarbon we use, it generates carbon dioxide with itself. But therefore hydrogen is very limited. And if you get the hydrogen, but just by splitting water, because water is combination of hydrogen and oxygen, so you can, if you can split the water and get the hydrogen from water, then it will be very economical. No, with very less investment, you can get hydrogen as a fuel and you can use it, which will not generate any pollution. That is a very desirable. Therefore, but this titania is therefore great to convert split water to hydrogen and oxygen. So it shows the mechanism how this splitting happens. So where is it not coming? Next slide. Okay, see, this meeting is going to end in 1 minute, because the limit we got in Zoom, that is 40 minutes. So let us discuss this one in the next day. Okay, so if you have any problem, you can ask me now.